Okay, guys, welcome back. So we are going to talk about percent composition now. So now that we've had a conversation about how we calculate a molecular mass and how we can deal with the masses that we're talking about, then we can talk about how we can do some calculations with those masses related to the molecular mass. First, we need to define a percent composition. So percent composition, percent by mass of each element in a compound, is the percent composition of an element. And so it's the number of that element times the molar mass of that element divided by the molar mass of that compound times 100. So that's our definition. So let's talk about that in terms of an example. So what's the percent composition of carbon in glucose? Now, glucose is C6H12O6. And so I want to talk about C6H12O6. So I want to know percent C, I'm going to do percent H, and I'm going to do percent O. And the reason I'm going to do them all is because why not? And I need to know the mass of all of them anyway. So I have 6 times the mass of carbon. I have 12 times the mass of the hydrogen. And then here I'm going to have 6 times the mass of the oxygen. Now I need to go find out what those masses are, right? So I'm going to come over here and look at the carbon that's present. I'm using this table. It's a little bit different than the one we have in the exam handouts, but it's the same idea. Mass that's listed here for carbon is 12.001. 12.011. 12.011. Now that is grams per mole. This technically is moles. So when I do that, that's going to give me grams. We're then going to divide this by the total mass. Now I'm going to calculate what that mass is. But right now, I'm going to calculate what it is from each of these things. So I want to know how much from the carbon I have. Now, I'll show you the rest of them in just a second. I want to take that 6 times 12.011, and that gives me 72.066. Didn't leave a lot of space, so that's 72.066, and that's correct. Okay. So I know that's the mass from the carbon. Now, let's talk about what we have from the hydrogen. Hydrogen is up here. He's 1.008. 8 grams per mole. So that then gives me 12 times 1.008. That then gives me 12.096 grams. Okay. We talk about our oxygen. We have 6 times the mass of the oxygen. Mass of the oxygen is 15.999. Again, mole here, moles here. 15.999 times 6 gives me 95.994 grams. And if I add all of those together, 72.066 plus 12.096 plus 95.4, I get a total of 180.156, and that's grams. Now, I can add all of those. And the reason I don't have to worry about that is because I have 3 decimal places here, 3 decimal places here, and 3 decimal places here. So when I do the addition, regardless of what happens on this end, because I added it on the same thing there, I'm fine because I still only have the 3 decimal places out here. Okay, so that's my total. And so each one of these is going to be divided by the 180.156 grams. Since this gives me grams on the top divided by the grams on the bottom, that means that that percentage is going to be unitless. So I'll take this number, divide it by that total, so 72.066 divided by the 180.156. Multiply that by, because that's what the formula says. And that tells me this is 40.002%. Is that a weird number? Sort of. Now, why am I reporting that as 5 sig figs? Well, this number right here is 5 sig figs. This number right here is 5 sig figs. This is actually 6 sig figs. And I know that my masses are technically infinitely known, but I need to cut off this percentage at some point. So we're reporting it to 5 sig figs because that's what we started with. Okay. So that one gets reported to 5. We then do the same thing all the way down. So I have the 12.96 divided by 180.156 times 100. It gives me 6.7112. 7142%. Okay. And then this one, 95. .994. I'll divide that by mass, which is at 180.156, and multiply that by 100. And then gives me 53.284%. And if I do just a rough check, that 40.002 plus 6.712 plus 53.284, I end up with 100.002, which to a very good approximation is 100%. So I'm happy with that. So that gives me the percent composition of carbon, hydrogen, and oxygen, and it all adds back up to 100%. That's what I'm looking for. So I can do a quick check to make sure that it comes back to 100%. If it doesn't, I did something wrong somewhere. So it's one of the ways that I can check my work to make sure that I've done the right thing. Okay. Questions about that? Now, I'm going to add another piece of paper so that I can get a little more space involved. I'm going to need to come back to look at what those other questions are about. It says, what is the composition of each element in ZN3PO42? Compound we're dealing with is ZN3PO42. So this is ionic compound, ZN3PO42. So the first thing I need to do is I'm going to look at percent ZN, percent P, percent O. So those are the atoms that I'm going to be dealing with. I know that I have zinc that appears in here. Let's go find our zinc. Is somewhere. Zinc go. At the moment, I cannot think of where he is. All screaming at me, going, "He's over there! He's over there! He's over there!" I'm sure. Zirconia, zinc. There we go. 65.38. There are 3 of those. And again, this is grams per mole. Times 3 moles. It's going to give me an answer in grams. 65.38 times 3 gives me 196 grams. If I look at my phosphorus, 30.974, 30.974 grams per mole times 2 of them. 2 moles. 61.882 grams. And then my oxygen, again, 15.999 should be that number. Yep, 15.999 grams per mole times, there's 4 there, times 2, that's 8 moles. 127.92 grams. Finding total, take the 196.14, I add the 61.882, and then I add the 127. It gives me a total of 386.014 grams. So I can take the 196.14 divided by 386.014 times 100. Set all these up. And that looks like it's already ready. So, hooray! So 196.14 divided by 386.014 times 100 gives me 50.81 and 1, 2, 3, 4, 5, 8, 1, 2, 2%. We now have that 61.882 divided by 36.014 times 100. That gives me 16.031%. And 27 divided by the 386.4 times 100, which gives me 33.157%. Technically, that should be 33.1573%. But to make it consistent with the other numbers, I'm just going to report it the way that I reported it. All right, adding all of those numbers together and quick check just to make sure I'm the same. I get 99.9999, which again is close enough to 100 for me to feel comfortable. So that's my percent of biomass for each of those components. Cool with that. All right. Now, there's one more thing that this piece of paper talks about, and it says we can use the same process in reverse to determine the empirical formula of a compound. If the mass percent of sulfur is 40.05 and for oxygen is 59.95, what's the empirical formula of the compound? So it says sulfur 40.05%, oxygen 59.95%, what's the empirical formula? So when I go this direction, we're going to make an assumption based on what I've been told. I'm going to assume that the total mass that I have is 100 grams. So if it's 100 grams, that means I have 40.05 grams of sulfur and 59.95 grams of oxygen. And again, total mass equals 100 grams. Right? Now, if that's true, I have 40.05 grams of sulfur. Find out how many moles I have, I would divide by the molecular weight. Weight of the sulfur is 32.06. 32.06 grams of sulfur and 1 mole of sulfur. .05 divided by 32.06 is 1.249220212 moles of sulfur. Okay. Now I had 59.95 grams of oxygen. That's what it says right here. Divide that by the molecular weight of oxygen, which is 15.9. So for 1 mole of oxygen, 59.95 divided by 15.999 gives me 3.747109114 moles of oxygen. And what I know, looking at an empirical formula, is that that is a ratio of the moles of those things, not the masses, but the moles. So I now have a relationship to know how many moles of each material that I have, but they're not nice whole numbers. So what I would be looking at if I were trying to do this way is sulfur 1.2497, and then oxygen 3.7471. Those don't work very well. So what I'm going to do is divide by the smallest number, 1.2497, and then 1.247. That would then lead to sulfur being 1 and oxygen, I take that 3.747 divided by that 1.249, that whole big number. And I end up with 2.99955857, which is enough to round that to 3. So I end up with SO. Wait. That's a nice formula, and I'm okay with that. Now, does it always come out that evenly? No, sometimes it doesn't. And sometimes we end up with like a 1.5. And so then I have to multiply everything by 2 to get a formula that makes sense. Okay, that is something that happens. We have to get to a ratio between those two things that works, and it's got to be whole number. Okay, so that's what we're talking about. So we take whatever percentages we're given, assume that that is a mass out of 100, convert that to a number of moles, divide by the lowest number, so that we are then trying to get a whole number ratio. And if that ratio looks funky, which it does, we divide by that lowest number and then see what it looks like. And we do whatever we can to make it look like a reasonable number. Okay? So 1 to 3 actually looked reasonable. So we just write that as SO3. Okay, so that's how we work with that. Questions, comments, problems? It's going to take a bit of practice. There is a bit of practice for you to do to be able to do this. Okay, so that's how we can take the data that we've been given to get to an empirical formula. So, a couple of things I want you to calculate. Percent composition of MgCl2, percent composition H2SO4, empirical formula, 40% carbon, 6.67% hydrogen, and 53.33% oxygen. And then empirical formula for a molecule that's 31.42% sulfur, 31.35% oxygen, and 37.23% fluorine. I'm going to come back to you in just a bit, and we'll see what we can do from here. Thanks, guys.